Students, today we will start with the photoelectric effect. So the photoelectric effect was postulated or discovered by Einstein in 1905. I should not say discovered, it was discovered earlier, but rather explained by Einstein in 1905. Einstein, who was one of the great scientists of the 19th century. So let us now start about the photoelectric effect. So basically, what is the photoelectric effect? Herein there is a metal plate that is often used as a cathode in a particular circuit. This metal plate is irradiated with photons of light. Photons are supposed to be light particles. So this metal plate is irradiated with photons. So as a consequence, what happens is electrons get emitted from this metal plate. Electrons that carry negative charge, they get emitted and they move at varying speeds. These electrons are collected by a positive electrode. Remember, negative charges are attracted by a positive electrode called as the anode. The cathode is depicted by the letter K, even though the spelling is CATHODE. The reason being, the letter C is used for current most often. So completing the circuit, often the voltage supply that is used is a variable voltage source, and the entire apparatus is kept inside an evacuated chamber or container. So this is the basic setup or apparatus of the photoelectric effect. I'll again recapitulate. Photons are being incident on a metal plate called as the cathode. Because of this is the cathode, the one highlighted in yellow, because of which electrons are emitted and electrons move towards the opposite terminal, which is called as the anode. Anode being positive, it will attract the electrons naturally, and cathode being negative will repel the electrons naturally. So once the electrons are emitted from the cathode, they will go towards the anode, and then via the anode they will travel inside the circuit as shown. So the green arrow represents the direction of travel of the electrons, and the blue arrow shows the direction of travel of conventional current. Let's move on to the next page. So what happens over here is that inside the cathode there are various atoms, right? So electrons are bound to the nucleus of the atom. So what happens is when the light comes in and falls on the outermost shell of these particular outermost atoms of the cathode, then what happens is light energy excites the electrons or gives them additional energy so that they can overcome the bound of the electromagnetic force of attraction by the nucleus. So because of that, the electrons move outside of the nucleus and are hence free from the cathode, and they are free to travel towards the anode. Why is the chamber evacuated? Why is this chamber evacuated? So that these electrons that come outside of the cathode do not encounter any air particles in between. Otherwise, they'll ionize the air and we won't be able to study or analyze the velocity of electrons, kinetic energy of electrons, and so on, which we actually want to do. That is why we have an evacuated chamber, and the electrons from the cathode would want to go towards the anode. Okay. So obviously there will be some electromagnetic force of attraction between the cathode atoms and the electrons. So the photon will have to have some minimum energy that it will need to kick away the electron from the atom. This minimum energy is called as the work function, or the threshold energy required to kick the electron outside of the cathode. Just imagine one scenario. There is a bucket kept over here. Alright. In this bucket are kept small marbles. Many of you might have played with marbles in your childhood. So small marbles are kept inside this bucket. Imagine that a person is going to throw a single big brick inside this bucket. And let us for now imagine that the brick is capable of displacing only one marble. So I am sure that you guys will agree that if the person drops the brick in very softly or slowly, then none of the marbles will spill outside the bucket. So the brick will have to have some minimum amount of kinetic energy that it should possess such that the marbles will be spilled outside. So this minimum amount of kinetic energy in this scenario is called as the threshold energy. So in our photoelectric equation scenario or the photoelectric effect scenario, this is the cathode, this is the anode, this is the evacuated tube, and this is the location from where the photons are coming. So the photons are supposed to have some minimum amount of energy. That minimum amount of energy is called as the work function. Okay. So the energy of the incoming photon, which is nothing but HF, this we have seen. HF is the energy of the incoming photon, right? So HF is equal to the work function plus what? Plus some quantity, right? So the photon will have energy that is required to overcome the attractive pull of the nucleus plus some extra energy it might have, right? So the extra energy goes where? It goes in the kinetic energy of the emitted electron. It is but natural. Half mv square. But here we will look at only the maximum kinetic energy electrons, not all or any of the electrons, but only the maximum kinetic energy electrons. There is a reason for that. Just imagine our bucket analogy. There are marbles over here and there is a brick thrown. Now this brick will go and hit a marble. So some of the marbles might come out directly. Some of the marbles might hit the surface of the container and then come out. Some of the marbles might hit only once and then come outside. So the marbles that are hitting other marbles as well as the surface, inner surface of the container in which they are kept or the bucket in which they are kept, these marbles are losing some energy and we do not know exactly how much energy they are losing, and hence we care only about the marbles that come outside directly. So if the marbles are coming outside directly, we know that exactly the energy that they possess is the energy equivalent to the maximum energy that can be possessed by any such marble that is coming outside. Similarly, this term hence corresponds to the maximum kinetic energy of electrons, because we don't care about the electrons who have lost their energy by colliding with other particles while coming outside. And hence the energy of the incoming photon goes in two ways. One method is to overcome, or one part of the energy goes to overcome the threshold or the barrier that is there because of the nuclear force of attraction, and the remaining energy is transferred to the electron that goes outside. So this is the maximum kinetic energy of the emitted electron. Okay, for this is the maximum kinetic energy electron that went directly outside. There might be some electron which will not be the maximum kinetic energy electron, for which the equation will be Hf is equal to W plus kinetic energy of that electron, okay, plus some wasted energy wasted, I meant, right? So this equation is true for all electrons. For the maximum kinetic energy electron, the wasted part of energy is 0, and for some other electron the wasted part of energy might be something which we don't care about that energy or that particular wasted part, because we don't know what it is and hence we can't measure it, so it's not useful for us. So what we will rather care about is this particular energy or this particular equation. Now, how to measure the maximum kinetic energy of the given electron? How can we measure the maximum kinetic energy? So it is simple again. What we will do is we will basically stop the electron using a potential or voltage. How can we do that? Remember that we already have this electron set up inside an electric field. So since the electrons are already set up inside an electric field, and remember that I told you that the supply is variable or the voltage is variable basically. So now what I can do is I can very smartly make the anode, that was the terminal that was earlier the anode, I can very smartly make it negative, and very smartly the terminal that was cathode I can make it positive. So the electrons have a natural kinetic energy tendency to move forward, but because of the electric field they have a tendency to move backward. The natural tendency is to move forward, and because of the electric field their tendency is to move backwards. And hence it is like exactly like a situation of a ball that is thrown upwards in the air. The kinetic energy of the ball is propelling it forward, and the gravitational pull of the ball is trying to move it backwards. So till what distance the ball will reach? It will reach a maximum height such that mgh is equal to half m v square. That is, the entire velocity of the ball or the kinetic energy of the ball will be converted into potential energy. Velocity will be converted into height. Similarly, in this case, the energy of the electron in an electric field is given as QV. Q being the electric charge over here and V being the potential. So this is equal to half m v square, and since we are talking about the maximum velocity, this is half m v max square. So this is E times V is equal to half m v max square. Therefore this will be E times V. This V is called as Vs, named as the stopping potential. Stopping potential. Why is it called as the stopping potential? Because guys, note that the electric field is stopping the maximum kinetic energy electron. That means it will be stopping each and every one of the electrons, right? If the maximum kinetic energy electron is stopped, all the electrons will be stopped. None of the electron will be able to come and hit the surface of the so-called anode. It's actually negative, but since we labeled it anode earlier, I am saying that this is the anode. Alright. And hence in this photoelectric equation what we will do is we will replace this equation HF is equal to W, and we'll replace the half m V max square term as E times Vs. This is what we'll do. Alright, so moving on to the next page. This is called as Einstein's photoelectric equation. HF is equal to HF naught plus E times Vs. So you can see that here I have replaced W with HF naught. So what does that mean? W is basically an energy. W is an energy. It has been replaced with HF naught. Meaning there will be some frequency F naught that will be equal to W, which is the energy required to pull the electron outside the nucleus. That frequency is called as the threshold frequency. That frequency is called as the threshold frequency. So this is another version of Einstein's photoelectric equation. So summarizing what all we wrote about the photoelectric equation, this is one form. Another form is HF is equal to W plus half m V max square. Another form is equal to HF is equal is another form is HF is equal to W plus E times Vs. So these are the three forms of Einstein's photoelectric equation. Okay.